instantaneous rates of change. By now, this should not be a problem for you. Right now, you should be able to tell me the difference between an average rate of change for a function and the instantaneous rate of change. And simply, the big difference is average rate of change is slope. Instantaneous rate of change is derivative. That's all it is. Okay? So, the instantaneous rate of change of a function with respect to x at a particular point that we'll call a is nothing more than the derivative. So this is one of the last times we're going to write this. The derivative of a function at a point a is equal to the limit as x approaches a of f of a plus h minus f of a all over h. From this moment on, when we ask you to find the rate of change of a function, we are asking you to find the instantaneous rate of change. We're no longer going to use the word instantaneous. They do not use the word instantaneous on the AP exam. So if they say find the rate of change, they're asking you to find the instantaneous rate of change. They're asking you to find the derivative of the function. If they want the average rate of change, then of course they'll use the term average rate of change. So you're looking for the word average rate of change or simply rate of change. So get that difference down. Something that once we get into the actual exam, in about the 1st of April, hopefully last of March, we'll start studying. That always comes up. What's the difference between the two? Rate of change, average rate of change. We've got the area of a circle represented as a function of the radius. The area of a circle represented as a function in terms of the radius of a circle. It says the area of a circle as a function of the radius is a equal pi r squared. Part A, find the rate of change. Find the rate of change of the area A with respect to the radius r. So we want to find the rate of change, the derivative, of the area with respect to the radius. So we would write it dA dr. That represents the rate of change, the derivative of the area function with respect to r. In other words, r is your variable. Everything else is a constant. So we would call this 2 pi r. The derivative of pi r squared is 2 pi r. Using the power rule, I take 2 times the constant times the base to the n minus 1 power. There is your rate of change, instantaneous rate of change. Part B, evaluate the rate of change of the area when r equal 4. When the radius of my circle is 4 units, then evaluating the derivative of the area, so I switched from dA dr to a prime r, where r is equal to 4, so I'm evaluating a prime of 4. So I take 2 pi times 4 and come up with my 8 pi. Suppose that an object is moving along a coordinate line. This begins a tremendous discussion about particle motion. You're going to feel for a while that you're in a physics class, but you're not. You're in calculus. I'm not teaching physics. I'm teaching calculus. But one of the main topics in the College Board really loves particle motion. The motion of a particle on a horizontal line. So suppose that we have an object that is moving along a coordinate line so that we know that its position function on that line is a function with respect to time. So we'll say that our position function is s equal f of t, where s is your position function. The displacement, there's a new word to put into your vocabulary, your calculus vocabulary. The displacement, the change in position of the object. Sometimes we call it a particle, sometimes we call it an object, okay? So the change in position of the object over the time interval. Over the time interval. From t to t plus the change in the time. So our definition of displacement, the displacement of a particle, is f of t plus delta t minus f of t. Average velocity, here we go with the physics, average velocity of an object over that time interval That's the way I write average velocity. Capital V with a subscript AV for average. Average velocity, by definition, then is equal to your displacement divided by your travel time. How far did it travel divided by how long did it take to make that travel, which is nothing more than the change in the position. Take on it. And we could represent that delta S over delta T, the change in position over the change in time, which we now know is equal to F of t plus delta t minus f of t all over the change in time. Average velocity. Well, if we have average velocity, average rate of change, do you not see that that's simply the slope formula? So don't get all hung up on the symbolism that we're using. As soon as you see average velocity, we're now replacing rate of change with the word velocity. That's all we're doing, okay? So the average velocity, excuse me, the average rate of change is still slope. It's always going to be slope. So if we've got average velocity, we would also have instantaneous velocity. But we know average and instantaneous aren't the same. Don't ever think that they are. So instantaneous velocity And again, we're not going to use the word instantaneous because we've dropped the word for instantaneous rate of change. We're going to drop it for instantaneous velocity. We're just going to call it the velocity. So the velocity, again, is the derivative of the position function. And your position function will always be s of t, and it's always with respect to time. So now if we give you a position function, we're going to ask you, find the velocity of that function. Find the velocity of that particle moving from left to right. Find the velocity of that particle going up and down. And your job is to remember, oh, piece of cake. That's just the derivative of the position function. That's all it is. Don't make it difficult. Now, what else? At time t, velocity. In symbolism, I like this the best. Velocity is nothing more than the derivative of the position function with respect to time. And of course, I thought I was done writing this, but whatever. And of course, that's just our definition of a derivative with respect to time. Right here's what you need to know. And the good news is, everybody always remembers this. You'll still remember in May that the derivative of the position function will always give you velocity. The derivative of the position function will always give you velocity. Now, besides telling you how fast an object is moving, velocity always tells you, or also tells you, the direction of the motion. Velocity does two things. It tells you how fast and what direction. If your velocity is positive, the object is moving forward. If you're on a horizontal plane, if your velocity is positive, it's moving to the right. If we shoot something up into the sky and it comes back down, if your velocity is positive, the object is going up. If the velocity is positive. If the velocity is negative, then you're moving backward. If you're on a horizontal plane, you're now moving to the left. If velocity is positive, it goes to the right, the particle. If velocity is negative, it's going to the left. And again, that's pretty easy to remember. So if we drive to the grocery store at 30 miles per hour, our speedometer will show 30 on the way, but it will not show negative 30 miles per hour on the way back, even though our distance from home is now decreasing. That would be too confusing for the American public if we had positive and negative values on our speedometers, okay? So it just says 30 miles per hour. The speedometer always shows speed, not velocity. And we define speed as simply being the absolute value of velocity. That's why we call it a speedometer in your car and not a velocityometer. Okay? It's a speedometer. We're talking speed. What is speed? Speed is the absolute value of velocity. Speed. Absolute value of velocity. is equal to the absolute value of your velocity function. Or if you prefer, the derivative of the position function with respect to time, the absolute value of that. And you got to get into the habit of seeing these two different symbolisms and knowing that they both mean the same thing. V of t, velocity with respect to time. ds dt, the derivative of the position function with respect to time, but we know that the derivative of the position function is the velocity function. Well, we've got a position function, we've got velocity, we've got speed. We also have something called acceleration. Acceleration. Acceleration, by definition, the derivative of velocity, again with respect to time. If a body's velocity at time t is v of t, which we know is the derivative of the position function, then the body's acceleration at time t is acceleration. We always represent that as a function a of t, which we know is the derivative of the velocity function with respect to time dv dt, or d squared s of dt squared, a higher order derivative. If you take the second derivative of the position function, you are finding acceleration. The motion of free-falling bodies with respect to the force of gravity, experimental and theoretical investigations revealed that the distance that a body released from rest falls freely. It's proportional to the square of the amount of time it has fallen. This is expressed as the position of a free-falling object. You're on the moon and you drop a rock down into a crevice or something, I don't know. S equals 1/2 g t squared. Again, the distance that a body released from rest falls freely is proportional to the square of the amount of time it has fallen. The square of the amount of time that it has fallen. S is distance. G acceleration due to gravity, and you science people already know that. And t is time. If t is with respect to seconds, we have two different models for free-falling objects. The English model is that S equals 16 t squared, and the metric, because of force of gravity, 4.9 t squared. S in feet, S in. But the good thing that you don't need to worry about, we will always give you the position function. I don't care if we're going left and right or if we're going falling. we will give you that. But I just wanted you to see, if your coefficient is 16 t squared, you're working in English measure. But if your coefficient is 4.9 t squared, then you're working with metric units, okay? Let's say a projectile is shot upward from the surface of the earth, and it reaches a height and its position function is given as s equal negative 4.9 t squared plus 120 t, and this is in terms of meters after t seconds. And of course, as soon as I see that negative 4.9, I know I'm working in the metric system based on what we just talked about. So, find the velocity of this projectile. Find the velocity after 5 seconds. You can't find velocity if you don't have the velocity function. We do not have the velocity function. We have the position function. But you have just been taught that the velocity function is the derivative of the position function. So I know that the velocity is equal to the derivative of the position function, which gives me what? Negative 9.8 t plus 120. There's your velocity function. And what do we want to know? We want to know what is the velocity at the instant 5 seconds. So I need to find v of 5. How do you evaluate? How do you find a function value? Of course, this is something that was taught to you back in first year algebra. That didn't sound right. First year algebra. So now you're going to start seeing, why on earth did you have to do the things you had to do in Algebra 1, Algebra 2, geometry, maybe even some pre-cal? Why did we have to do those kind of things? So we can do this cool stuff. So we can do the calculus. So evaluate your function, your velocity function at t equal 5, and we come up with 71 meters per second. Remember, velocity is a derivative. Velocity is a rate of change. So your label for the velocity has to represent something compared with something else. In this problem, we're comparing meters to seconds. It's a rate of change. It's an instantaneous rate of change. No, this is called velocity now. I have a stick of dynamite, and I blast a rock up into the air, straight up. And the launch velocity is 160 feet per second. That's about 109 miles per hour. And it reaches a height of 160 t minus 16 t squared after t seconds. Part A. How high does the rock go? And all I have is is my position function? I have a rock. And apparently some way we took this big heavy rock and we put some dynamite underneath it. And then we lit it. And the rock goes up to a certain height. Then of course it's going to turn around and come back towards Earth. I want to know what is the maximum height of the rock. When it reaches the maximum height, what's the velocity got to do? As it's going up, and then it's going to come back down. At that moment, it changes direction. It stopped, didn't it? For just a split second. Meaning that the velocity would have to be equal to 0 at that maximum height. So all I have to do is find the velocity of this function and set it equal to 0, and that will tell me when it reaches its highest point. Now please note, I didn't ask you when it reaches the highest point. I want to know how high does it go up. So once I find at what time it's at its maximum height, I take that time and do what? Put it back into the position function, right? So easy peasy. The velocity with respect to time is equal to 160 minus 32t. There's my velocity function. And we just said the velocity will be equal to 0 at that instant the rock has reached its maximum height before it starts coming back down. So we're going to take the velocity function and set it equal to 0. So we have 32t equals 160, t equal 5 seconds. So at t equals 0, we shoot it off. In 5 seconds, it has gone as high as it's going to go. It's going to now turn around and start coming back down. So at t equal 5, I want to find the position. So now I need to find s of 5 by taking 160 times 5 minus 16 times 5 squared, and that gives me let me check my arithmetic. I think it's 400 feet. Part B. What is the velocity and speed What is the velocity and the speed when the rock is 256 feet above the ground? When it's going up and going down. So in other words, we shoot the rock up, and somewhere going up it's going to reach 250 feet, or 256 feet, I guess. And then it's going to go on up to this maximum height of 400 feet, and then it's going to come back down. As it's coming back down, it's going to be at 256 feet for just a moment. And we want to find what is the velocity at 256 feet and what is the speed at 256 feet. Again, kind of like this problem, first thing you got to do is find when it was at 256 feet. Because if I can find when it's at 256 feet, then I can plug that time into the velocity function. Because the velocity function is with respect to time, then I can find at what the velocity is at that time, at that moment. So what we're going to do is we are going to take the position function of 160t minus 16t squared, and we're going to set that equal to 256. Which is going to give us a positive 16t squared minus 160t plus 256. equals 0. I have to solve a quadratic formula, or a quadratic equation. Or I could use a formula, but I always try factoring. Looks like I can factor out a 16. So I factor out a 16, I get t squared minus 10t plus 16. Factoring, I get t equal negative 2, t equal negative 8, or t minus 2, t minus 8. Divide both sides by 16. So at t equal 2, and at t equal 8. So going up after 2 seconds, after you blow the rock, after 2 seconds, it's at 256 feet. Then it goes on up to the 400 feet, and then at 8 seconds, it's now on its way back down, and it hits that point again at 256 feet. What?
Why did you change the negative sign from the negative 16t squared to the 100?
I just took everything over here to the right-hand side, because when I factor a quadratic function, I always want the leading coefficient to be positive.
Okay.
It just makes it simpler.
Okay.
Yeah, you could factor it with a negative coefficient, but it hurts my brain to do that, so I just don't do that. So like we said, now we need to find the velocity at t equal 2. We need to find the velocity at t equal 8. So we're going to evaluate the velocity function at 2, and we already know that the velocity function, we already found that in part A. So we're just going to simply take 160 minus 32 times 2, and we come up with 96 feet per second. And 160 minus 32 times 8, we get negative 96 feet per second. So there's the first part of that problem. The velocity when the rock is going up and it hits 256 feet, the velocity is 96 feet per second. Coming back down at 8 seconds when it's at 256 feet again, the velocity now is negative 96 feet per second. The negative sign simply tells us that the rock is going down. But we also want to know the speed. Speed is the absolute value of velocity. Feet per second. And I'm so out of time. I guess I'll save the rest of the problems for another day. Your homework assignment for tomorrow.